Alright, before we go into the main content, here's a question. So let's say Christmas is coming soon, you have decided to need scarves for your friends and intend to hand them out during a Christmas event. You currently have 13 balls of yarn and each scarf needs 3 balls of yarn. How many scarves can you make? So it's a pretty easy arithmetic question. So you just take 13 divided by 3, which gives you 4 and 1 over 3. 1 over 3 means it's not a whole scarf, so your answer to the question would be you can make 4 whole scarves. Easy. Now if we extend the question and say that we want to make a program, then take in your number of balls of yarn as an input and another input, which is your number of balls of yarn needed to make a scarf. And then we use the division algorithm to get maybe an output, where the output would be basically just this, which is basically 4.3. 333. Yeah. And now you have this as your output, right? But your answer is 4. Let's say you want your answer to be 4 instead of this. So how would you program it? Well, apparently there are functions for it, which is called floor and ceiling functions. So basically this is the floor function and this is the ceiling function, denotations. Alright, so yeah, this will be the main topics we'll be talking about. So here's a bit on the origin if you are interested, but we'll be skipping it due to not enough time. Alright, so this is the definition of a floor function, where its domain is the set of all real numbers and the codomain or range is the set of all integers. So its definition says that it assigns any real number, call it x, with the greatest integer that is less than or equal to x. So if we look at the graph, we can see that if it's 0, it's 0, if it's 1, it's 1, it's 2, it's 2. So basically if also look like negative 2 is negative 2, etc. So if it's an integer, therefore the function will just return you the integer. However, if it's not an integer, notice that everything between 0 to 1 is just assigned to 0. This is because 0 is your greatest integer. That is less than 0. That is less than all numbers within 0 to 1. And then the same can be said for the other integers. Alright, now for the ceiling function, it's about the same as the floor function, where its definition would be assigns any real number x with the smallest integer that is equal to or more than x. So we look at the graph again. The same can be said for the ceiling function. Integers will always be assigned to integers, no problem. Where instead, for ceiling, the numbers between 0 to 1, they will all be assigned to 1. So basically, it's the smallest integer that is greater than x, which is like all of these x's. The smallest integer that is greater than this guy is 1. Therefore, all of them are 1. Okay. Now we're done with it. Alright, so let's come down here. So here are two common equivalences for the floor and ceiling functions. So we won't delve too deep into them because we won't have enough time, but basically let me just tell you what does this mean and basically what does this basically means. So for this with upside down a, basically it means for all of the x's which within the set of real numbers, which means like x can be a fraction, a decimal, or a rational number. Rational number. Then the equality here holds. And then for the bottom one, it says that for any x that is equal to n plus y, where n is an integer, and y is within the interval of 0 to 1, which basically means y will be a fraction, or a decimal, or a irrational number, then this equality holds. Where basically, like, this is saying that the what do you call this? The floor and ceiling function, they don't affect the integers. They only affect the fractional parts. Yeah. Alright, next. Okay, so basically, yeah, the applications, which will start here. So come back up again. So this is the pigeonhole principle, and if you don't, if you have no clue what it is, I would need you to pause and actually have a look at this part first. So yeah, do that, and within 3, 2, 1, right? So if hopefully you understand the pigeonhole principle. So below here we have the generalized principle, which is basically where we could use it for more cases than just only k and k plus 1 and k. So if n pigeons are placed into k pigeonholes, there is at least a pigeonhole containing at least n divided k ceiling pigeons. Note that n, k, and also these two k's are all integers. However, n divided by k is not necessarily an integer until we use a ceiling function. Alright, so here's a quick example where we can use the generalized pigeonhole principle, which we would be using the ceiling function in a bit. So let's say that Santa's factory has met with a disaster. His toy making machine malfunctioned in such a way that it can only make either 1 out of 5 distinct toys in random every time. So how many toys would he need to assure that he can have at least 29 of the same toy ready? So here is how you would apply the pigeonhole principle for this question. So let's call the number of toys, so how many toys he needs. So we call this as n. So the pigeons here is basically the number of toys he needs. Number of toys needed, which is n. And then here the pigeonholes would be the 5 distinct toys. 5 distinct toys. This one. So basically we want to have at least 29 of the same toy ready. So therefore by the pigeonhole principle, well, the generalized one, we want n divided by 5 ceiling to be greater or equal to 29. Now, note that this is not your normal arithmetic operation. So what you need to do is you want to use this. So we know that x plus 1 is greater than the ceiling of x. So this implies that n over 5 plus 1 is greater than n over 5 to ceiling. Therefore, we plug that into here, and we would get n over 5 plus 1 is greater than 29, which implies that n divides 5 is greater than 28, which means n needs to be greater than 5 times 28. Therefore, if n needs to be an integer, n is greater than 5 times 28, therefore n has to be greater or equal to 5 times 28. 29. No. 28 plus 1. It will have to be this number. N has to be at least 5 times 28 plus 1. So yeah, that's how you would deal with this kind of operations. Alright, we're running out of time. So back to our very first question. To have the code output integer instead of a float, which is like the decimal earlier, 4.3333, we can just do this. We use the floor function, and we call 13 divided by 3 as v, and then we put it into the floor function, and then we just print it. Therefore, it will just output 4. Now, do we still have time? Alright, just in case we don't have time. So this question, try doing it, and give it a pause and just do it. So I'll give it 3 seconds. So 3, 2, 1. So here's the answer. So there's a total of 29 people in the class, and you have 5 keychains per packet. So the number of packets you should get is 29 divided by 5, and you will need it to be in ceiling. Is it? Yes, ceiling. Oh wait. Yeah. My bad. Ceiling. So basically, 29 divided by 5 is 5, and 5 plus 4 over 5, which is basically 5 plus. So the ceiling of this is basically just 1. Therefore, your answer should be 6. You need to get 6 packets. So yeah, thanks for watching, I guess. And yeah, it's Christmas today, so Merry Christmas and see you.